X-ray diffraction is the most important experimental technique in the investigation of crystal structure of solids. It is also one of the chief experimental tools in working out the double helix structure of DNA and subsequent advances in molecular genetics. The discovery of DNA is an important scientific achievement. It involved scientists from countries like England, USA, and Czechoslovakia in the 40s and 50s. There was fierce competition as to who would be the first to make the discovery. Watson and Crick were eventually the first to discover the structure of DNA molecule using the stick and ball model. Other scientists used experimental approach instead. Among them were Franklin and Wilkins, who used X-ray diffraction to understand the physical structure of the DNA molecule. Franklin's photograph above shows the diffraction pattern produced when exposing a sample of DNA to X-rays. Franklin and Wilkins' work using X-ray diffraction was groundbreaking, although they were not able to fully interpret their results. Crick and Watson were able to deduce the three-dimensional double helix structure from the X-ray diffraction photograph. Crick, Watson, and Wilkins all shared the Nobel Prize for the discovery. Unfortunately, the brilliant female scientist Franklin died before the prize was awarded. Introduction to X-ray diffraction. In this lesson, you will learn X-ray diffraction. To derive and use Bragg's equation, 2d sin theta equals m lambda. When X-rays were first discovered in 1895 by Wilhelm Röntgen, their exact nature was not known. Hence, the name X-rays was used. The wave nature of X-rays was verified by the X-ray diffraction experiments performed in 1912 by Friedrich Knipping and Max von Laue. Diffraction patterns were observed in the experiments. X-rays are electromagnetic waves of wavelengths in the order of 0.1 nanometers. Click the X-ray tube to observe the path of the X-ray beam. Click the crystal button to insert a thin crystal in the path of the X-ray beam and observe the changes. Click the diffraction button to view the diffraction pattern. The lattice atoms in the crystal are arranged in a regular pattern, and the atomic spacing is about 0.1 nanometers and is comparable to the wavelength of X-rays. Thus, crystals can act as a three-dimensional grating for observing the diffraction of X-rays. Can X-ray diffraction pattern be produced using an optical diffraction grating? Answer: no, the wavelengths of X-rays are too small for the optical diffraction grating to produce a noticeable diffraction pattern. Summary: X-rays are electromagnetic waves of wavelengths in the order of 0.1 nanometers. Crystals can act as a three-dimensional grating for producing X-rays diffraction. Diagram shows the crystalline structure of sodium chloride. The sodium ions and chlorine ions are arranged in an orderly manner. There are many different families of crystalline planes which can serve as a three-dimensional diffraction grating for X-rays. Click the Family 1 button, the Family 2 button, then the Family 3 button to view 3 different families of crystalline planes. When an X-ray beam is incident on a crystal, the X-rays are scattered, absorbed and re-emitted in all directions by the atoms in the crystal. In some directions, the scattered waves undergo destructive interference. In other directions, the interference is constructive. This process of scattering and interference is a form of diffraction. Constructive interference occurs in directions as if the X-rays were reflected by a family of crystalline planes. The X-rays are actually diffracted, but the term reflected X-rays is commonly used. When X-rays are incident on a crystal, they can be diffracted from many possible families of crystalline planes. Although the process of diffraction of X-rays by a crystal is complicated, the maxima turn out to be in directions as if X-rays were reflected by a family of parallel crystalline planes. The X-rays are not actually reflected. We use these fictional planes only to simplify the analysis of the actual diffraction process. The angle between the incident ray and the corresponding crystalline plane is called glancing angle or Bragg angle. The distance between 2 consecutive crystalline planes is called interplanar spacing. Click any one of the diagrams to view the glancing angle theta and interplanar spacing d. Summary. There are many different families of crystalline planes which can serve as a 3-dimensional diffraction grating for X-rays. The angle between incident ray and the corresponding crystalline plane is called glancing angle or Bragg angle. The distance between 2 consecutive crystalline planes is called interplanar spacing. A beam of monochromatic X-ray of wavelength lambda is incident at a glancing angle theta. The interplanar spacing is d. The reflected rays from 2 consecutive crystalline planes are as shown. Click the derivation button to obtain Bragg's equation. First-order diffraction is observed when a monochromatic X-ray beam is directed at the glancing angle of 26.5 degrees as shown. The interplanar spacing is 0.26 nanometers. A. At what glancing angle will the second-order diffraction be observed? B. What is the wavelength of the X-ray? Click the solution button to check your answers. A monochromatic X-ray beam is incident at a crystal. If the interplanar spacing of the crystal and the wavelength of the X-ray is 0.35 nanometers and 0.25 nanometers respectively, how many orders of diffraction can be observed? Click each step to check the answer. Summary. Bragg's equation is 2d sine theta equals m lambda. Maximum orders m of diffraction is given by m is less than or equal to 2d over lambda. Maximum value of sine theta equals 1 and m is an integer.